All right, we got 2 more videos to do. This is 2.4. We're looking at, in this video, video C, we're going to do continuity over an interval, not just a point. And to lead with this, we're going to say 2 things. F of x is a continuous from the right at a if the limit as x approaches a from the right, or the positive side of f of x, equals f of a. So we've got continuous from the right, and it's coming from the positive side. And then we'll say b, it's continuous from the left at a if, and then we're going to do it from the left side, which is the negative side. The limit of x approaches a from the left equals f of a. So left, and that's giving us our negative side. We did one-sided limits already. This is not a new step, but we haven't looked at continuity before. Okay, so some more things to know real quick. This AB is called an open interval. It looks like a point. It really sucks. This part of math sucks. This is A is less than X less than B. And then if I have bracket A, bracket B, this is called a closed interval. And it has the included values. And then we have ones that we could include A but not include B, or use parentheses on A but use a bracket on B. So this should look more bracket-like here. These are brackets, the square ones. This is like A is less than or equal to X less than B, or A is less than X less than or equal to B, the way I wrote it. So on the open interval one, the open one, f of x is continuous over an open interval AB. If it is continuous at every point inside AB. That looks like a 6. I need to make it look like a B. And then we're going to say it's continuous on a closed interval. I wanted to do a different color here. This is where we have the brackets. First off, it has to be continuous everywhere inside, just like the other one. It has to be continuous from the right at x equals a, and it needs to be continuous from the left at x equals b. And we can mix and match these for like the other ones. The one on the right, the bracket a comma b needs this one. And the continuous from the left, the a comma b bracket needs this one, even though it's not really a closed interval. So also these. So let's take a look at some examples. Let's find or state the continuous intervals. I'm going to do f of x equals x plus 3 over x squared minus 4x plus 3. Now you can't cancel out the 3's because the addition sign's screwing up, but we can factor. So f of x is x plus 3. If I factor the bottom, I get x minus 3 and x minus 1. Which means we are discontinuous, or we have vertical asymptotes wherever the bottom equals 0. Okay. And that means those are the only values we can't use. So I'm gonna cross them off. I'm gonna say x cannot equal 3, x cannot equal 1, which means our continuous regions, they start at negative infinity, they go up to 1, and then we use a parentheses because we're not including the 1. I'm going to say in union with 1 to 3, and then in union with 3 to infinity. Let's say that was problem 1, or A. Problem B, let's take a look at f of x equals square root of x minus 2. Now, this is, again, we have to pay attention to what the domain is. So the domain for this, domain for a square root, an even square root, even nth root, where n is even. It's not actually, it's called the radical, radicand inside. The radicand has to be greater than or equal to 0. So we're gonna take that. Our radicand is x minus 2. We're gonna say x minus 2 is greater than or equal to 0. Add 2 to both sides, and we get x is greater than or equal to 2. Okay. So when we write this in interval notation, it can include the 2. So we're going to say, we're going to have 2 like that, and it's going to go up to infinity like that. So we're going to say it's continuous on 2 to infinity, including the 2. Finally, we will take a look at one more here real quick. Let's say f of x equals square root of x squared minus 1. So x squared minus 1 needs to be greater than or equal to 0. And if we factor this, we get x minus 1, x plus 1 is greater than or equal to 0. I'm pretty sure we did some number line stuff before. I'm going to put a point at -1 and a thing here at 1, and we're just checking these different regions. If I plug in 5, I get a positive and a positive, so this is positive. If I plug in 0, that's between -5 there. No, that's, yeah, those are both negative. I get two negatives, which make a positive. There we go. Negative times a negative is a positive. Here, if I plug in 0, I've got -1 times 1, which is -1. So this region is negative. And if I do like 5, I get positive and positive. So this region is positive. We're looking for things that are positive for greater than 0. So we want this region and this region. And we can include the endpoints because we have that equal portion. So here we're going to have -infinity to -1, bracket this time, and union from 1 to infinity. If you take a look at the textbook does a cool one like this. F of x is square root of 4 minus x squared. And here it ends up being only positive in the middle. So it ends up being -2 to 2. Let's see, what else we got here? One more idea in this little section, continuity. And then I got to do intermediate value theorem. It won't be another video. Composite functions. This is where you stick one function inside another. If I take g of x and put it inside of f of x, right, like inside, like replacing that, it's written as f of g of x. That's a composite function. So the rules regarding limits and continuity here, if f of x is continuous at L, and the limit as x approaches a of g of x equals L, then the limit as x approaches a of f of g of x equals, we can pass the limit inside which equals f at L. I guess I didn't need another line for this, because this portion here is right there. So we know that's L, so we get f of L. We've used this a little bit without really explaining it before in the last section. I could do limit as x approaches 0 of sine x equals sine of the limit as x approaches 0 of x, which equals sine 0, which equals 0. So this, there's a nice little trait here. This, testing this on all the trig functions, shows that trig functions are also continuous over their entire domain. All right, we got one more video. It's called the intermediate value theorem. I'll do it separately. It's kind of neat. Let me pause the video.